Good morning, ladies and gentlemen. Welcome to this discussion on Worksheet 6. You should have the worksheet as well as your solutions to the problems with you. Remember that you will not master maths by watching other people do it. You have to do these problems on your own. So let's have a look at the first question. Most students are baffled by the way that z is defined in this equation. We can make it look much better by using two substitutions. So, let x be equal to the root of t and let y be equal to negative 1 over t. Then we have z equals a function of x and y, with x equals to the root of t and y equals to negative 1 over t. We can now describe the relationship between the variables with this diagram that I've drawn on the right hand side of the screen. We also refer to that as a tree sometimes. The diagram simply says z is a function of x and y, two variables. X and y are each a function of only one variable, namely t. This is probably a good time to talk about the notations that we use when we talk about derivatives. When do we use the normal d and when do we use this curly d? We use the normal d when the function has only one variable. Otherwise, if the function has more than one variable, we use the funny d to indicate that it's a partial derivative. So, have you noticed that actually on the worksheet there was a typo? The question read, find partial derivative of z with respect to t, which if you look at the diagram on the right of the screen is incorrect because z is ultimately just a function of one variable t. So it should have been normal derivative of z with respect to t. We can now apply the normal rule to find the total derivative of z with respect to t by following in the diagram each path from z to t at the bottom. So we need to find the derivative of z with respect to x multiplied by the normal derivative of x with respect to t, or total derivative, plus the partial derivative of z with respect to y times dy dt. And then we can simplify this. We do not have a formula for f or for z in terms of x, so we leave dz dx as it is. The x dt we can actually calculate, and you can go and verify this. That will be 1 over 2 times the root of t, plus again dz dy we cannot calculate. The formula wasn't given, so we leave it as it is. But we can find the derivative of negative 1 over t, which is 1 over t squared. This is the final answer for question 1. Now let's have a look at question number 2. The first thing that you need to understand again is the notation. What exactly do we mean by the second derivative of z du dv? Well, it's defined as follows. The second derivative of z du dv actually means the derivative with respect to u of the derivative of z with respect to v. So you must be very clear. It means that you must first find the derivative of z with respect to v. That is the variable on the right hand side in the denominator. And after that, you find the partial derivative of the answer with respect to u. That is the variable on the left in the denominator. The diagram on the right hand side of the screen shows the relationship between all the variables. Z is a function of two variables, x and y and y in turn are each also functions of two variables, u and v. We can now write down an equation for the partial derivative of z with respect to v. Again, we need to follow each path from z down to v at the bottom. So the formula tells us it must be dz dx times dx dv plus dz dy times dy dv, and all of these are partial derivatives. In the next step, we calculate all the partial derivatives and simplify. I have moved up our last answer just to make some space on the screen. You need to study this equation for the partial derivative of z with respect to v carefully. Can you see that dz dv is a function of x and y, but also a function of u and v? The relationships are shown in the new diagram on the right-hand side of your screen, and this allows us to then write down the formula for the second derivative of z, first with respect to v and then with respect to u. Look carefully at this equation and make sure that you understand where each part of it comes from. Basically, we have to follow the paths from dz dv at the top of that new diagram down to u at the bottom. In the next step, we calculate all the partial derivatives, and then we simplify the expression and keep in mind that x and y were given in terms of u and v right at the beginning. Since all the functions are given in this example, there is also an alternative way of solving this problem. Let's have a look at that. By substituting the expressions given for x and y, we can directly express z in terms of u and v, as I've demonstrated here. We can now find dz dv directly in terms of u and v. Finally, we calculate the partial derivative with respect to u of the partial derivative of z with respect to v and get the same answer as before. Okay, let's have a look at problem number 3. If you look at what you need to prove, you should realize that there is no formula given for z in terms of x and y. It's simply stated that z is a function of x and y. So you cannot compute the partial derivative of z with respect to x, and you cannot compute the partial derivative of z with respect to y. So what to do? Well, let's start with the right-hand side. The relationship between the variables are given by the diagram on the right-hand side of the screen. Z is a function of two variables, x and y. X and y are each also functions of two variables, s and t. So we definitely can compute the partial derivative of z with respect to s and the partial derivative of z with respect to t. Let's do that. We cannot compute dz dx nor dz dy but we can compute dx ds, which is just 1, and dy ds, which is also just 1. We can now also calculate the partial derivative of z with respect to t. Again, using the tree, we must follow the path from z down to t at the bottom, and we get dz dt is dz dx times dx dt plus dz dy times dy dt. We cannot calculate dz dx and dz dy because there's no formula given for that, but we can calculate dx dt, which is 1, and dy dt, which is negative 1. The result now follows by simply taking the product of these two partial derivatives that we've calculated. I leave you to verify those calculations. Okay, let's talk about problem number 4. As before, we are going to use two substitutions to simplify matters and to get a clearer picture of the problem. If we use the substitutions u equals x plus a times t and v equals x minus a times t, we can draw the relationships as I've indicated with the diagrams on the right of the screen. We can now find a formula for the partial derivative of f with respect to t, namely df du times du dt plus dg dv times dv dt. We cannot compute df du and dg dv because there's no formula given for that, but we can compute du dt and dv dt. That gives us the following. We can use this last equation to find the second derivative of f with respect to t. That gives us the following. I'm going to erase the bottom part of the screen to create more space for the rest of the problem. We again use the diagrams on the right to write down a formula to calculate the partial derivative of f with respect to x. That is the derivative of f with respect to u times the partial derivative of u with respect to x plus the derivative of g with respect to v times the derivative of v with respect to x. We cannot evaluate df du and dg dv, but we can evaluate du dx and dv dx. These are both just equal to 1, so we get the following. We can use this last equation to calculate the second derivative of f with respect to x, and we find the following. The final result now follows from the two expressions we've developed for the second or the partial derivative of f with respect to t and x, as I've shown here. Okay, we're on to the last problem, number 5a. For this part of the exercise, you need to look at theorem 92, which is given on the worksheet and obviously is also in your lecture notes. The format that's given on the worksheet is in general for a function of n plus 1 variables. We will be using a special case for this problem where we only have 3 variables. So let's start with the following. Let capital F, which is a function of x, y, and z, be equal to that polynomial that we've written down there. What we want to do is apply theorem 92 to this function with 3 variables. Now we need to check all of the conditions of theorem 92. The first of that is we need to establish whether the first or the partial derivatives exist and are continuous. So let's first calculate the partial derivatives. See if you agree with my calculations of the three partial derivatives. Since each of these partial derivatives are polynomials, it follows from the discussion at the end of chapter 2 that all of these partial derivatives are continuous functions. The next condition that we need to check is we need to find the value of the function at the given point, which must be 0, and we must find the value of the partial derivative of f with respect to z at the given point, and that must not be 0. Let's do that. Check to see if my calculations are correct. Since the first or the partial derivatives are continuous, the function value at 2, 1, negative 2 is 0, and the function of the partial derivative at that point is not 0, we can apply the implicit function theorem. That means the following. This concludes our answer for question 5a. Let's do 5b. Using the results we found in 5a, we can immediately write down an expression for the partial derivative of f with respect to x and y, as I've shown here. Using these expressions, we can now calculate the value of those two partial derivatives when x is 2 and y is 1. I leave you to verify that my calculations are correct. That then is the end of problem 5b. For problem 5c, let us recall the result that we showed in 5a. We used the implicit function theorem to show that the equation fxyz equals 0 determines z as a differentiable function f of x and y near the point 2, 1, minus 2. Now, since f is a differentiable function, if you look at definition 73, that guarantees that the tangent plane to z equals fxy exists at the point 2, 1. Also, if you look at remark 74, we get an equation for the tangent plane, and then using the results in 5a and 5b, we can simplify this equation. And that ends this discussion of Worksheet 6. Keep well and stay safe.